Hello guys, Fru here. Welcome to the lecture for today. So today we're going to talk about some very elementary concepts in machine learning that are pivotal if you're going to study the concept. And my goal is to provide very intuitive understanding of the terms and the definition of those terms. This is something that could be very confusing for folks that are looking to get into deep learning, machine learning, AI in any capacity. So what are we going to look at today? We're going to look at deep learning. Let's get that pen straight. So we're gonna look at deep learning, and this is a series that we're doing around deep learning, but more specifically, the things we wanna uh, pay attention to or define is the concept of scalar vectors as well as matrices and tensors. So let's just write them all down. So scalars, vectors, matrices, and tensors. So if you're working in machine learning at some point, you're gonna come across this. Now, I'm a little bit fortunate that my background in undergraduate was in mathematics, so I do have an appreciation. I would say an elevated appreciation of these concepts. And even though today I'm not a practicing data scientist or a practicing machine learning expert, but this intuitive understanding from my background, I think, has been very helpful for me to grasp the concept. And that's what I'm going to hopefully do today in sharing this and providing definitions on these terms. So if we go back, and I just usually like to draw this circle of insight. So if you remember this circle that a lot of us are familiar with by now, is you have AI somewhere here, which is artificial intelligence, and then somewhere here you have machine learning, and then in here you have deep learning. So this is what we're talking about. Neural networks and CNNs and GANs and a lot of things that are happening inside of the deep learning space. And then even basic machine learning with statistical methods is popular out there. And then if you look at AI as a whole, which is an umbrella to all of this, you're going to run across these terms: vectors, scalars, matrices, tensors. Now, the reason why we're going to define this today is you can honestly, in making this video in 2022, whenever somebody's watching this video, there is an argument that you can do some really exciting machine learning without understanding what a vector or a matrix or tensors are. But if you're gonna go beyond the surface and start understanding what's going on underneath the scenes, you're gonna want to know what the matrix is, or what a vector or scalar and all of those things are, or what tensor is, right? And some people might know tensor from TensorFlow. There is a mathematical definition behind that. So let's dive right into our definitions. And we're gonna start with the very first one here, which is a scalar. What is a scalar? Now, in mathematics or even in computers, let's take a pen here. A scalar is, at the very simple term, if my pen is going to behave itself, a scalar is a value. So if you say I have a scalar value or a scalar variable, it's or you can say variable is just one thing. So let's say x equals 1. That's a scalar value. It can only occupy, it's just one instance of it. Now, on the mathematical side of things, of defining this, is it takes just one dimension in the vector space. So if you think about a number line here, and we had a number line, so a real number line. We start with 0, 1, 2, 3, 4, and we can count all this way back. So this is a positive, so 1, 2, uh, all the way to infinity. Let's go infinity this way, and then we'll go all the way to negative infinity this way, and we'll go in negative 1, negative 100, and we're going all the way to negative infinity on the other side. A scalar value can only occupy one spot on the number line. So it can either be a spot here, it can be a spot here, it can be a spot here, it can be a spot here. So In the vector space or in the number line, we will say a scalar is a one-dimensional vector space. So this is 1D vector space, right? So in the very elementary definition of it is something that can take one value. So a scalar is one value. Now, in the mathematical definition is if you think about a vector space or a number space, and I know we haven't defined vector yet, so I shouldn't even use that in my definition because we're building to that. So let's not define things with things we have to define. So let's just go back to, if you think about a number line like this, a scalar is something that can occupy any spot on this number line, right? So this is one dimension. That's why it's a 1D dimensional vector space, is because you have just one dimension, which is this. There is no, if you remember in basic math, you have like a one dimension. This is your x-axis, and another dimension could be your y-axis. Well, in this case, we don't have the y dimension, right? We just have the x dimension. So that's why it's one dimension. You can only go on this line, and you can occupy one spot at any point in time. And this could be a real number, it could be integers, it could be decimals. It doesn't matter what the spot is, right? So this is just the real number line, so it encompasses everything. We're not just talking about integers here. So that's what the scalar is. It can occupy one value in the vector space. So it's a one-dimensional vector space, or again, I'm still using the vector space here to define it, so just bear with me. Now, what could you use a scalar for? So let's say you're writing a program and you have the age of a person. Well, that's a scalar value, right? Because if your age is let's say 105, right? Don't ask me why 105, but if somebody is 105 years old, that you can only have one value for the age. You can have 105 and then 19 or so at the same time. It just doesn't work. So you need a scalar value to represent that. So that's a very common example of a scalar. So if you ever hear of scalar, that's basically what it means. Um, it can occupy just one value at a time. Now, building on a scalar is the next algebraic structure, or the next uh, thing we have to look at, which is a vector. Now, in data science and machine learning, you're going to come across a vector every now and then. Now, what is a vector in the definition of it? There are a couple of ways we can define this. And I'll start with the intuitive one, and then you might see one where the textbook will put that for us, the definition you might find in the textbook. So the very simple vector is points in an n-dimensional vector space. And I'm going to explain what we mean by that. So these are points in an n-dimensional vector space. All right. Okay. So you might say, well, I think I should not do vector space because we can't take vector space to define the vector spaces in an n-dimensional space. So points in an n-dimensional space. And here's a very simple example. Let's say we have some value x, and we want to define a vector of that. You have, let's say, x1, x2, x3, x4, all the way to xn. All right. So this is one. So this definition here is a definition of a vector, right? And what's the dimension? The dimension is n. So a vector can occupy it's just a points, a collection of points. And so these are points in an n-dimensional vector space. So the vector space here, or in an n-dimensional space, the space here is n. The dimension here is n. Now, the more technical definition we might give for this, and something that you might find in a textbook, either on the mathematics side or on the computer science side, would be something you might see. So this is our first definition. So let's go with the second definition here, would be n tuples of other sets of arrays, right? So you can say these are n tuples, and a tuples is just a collection of points or of numbers, but we want to have so n tuples of ordered. So the set needs to be ordered. There has to be some order to it. Set or arrays. So it can either be a set or an array of n numbers. All right. So again, so if you think about this bracket here being our set, so if you think about this bracket being a set, it's an ordered set. So 1, 2, 3, 4, 5, all the way to n of n numbers. So there are n numbers in that set. So think about it as a basket or a bucket of n number of things in which you can order those things inside. That's basically what a vector is. And this is the basic definition. But if you want to look at the intuitive definition where we talk about points, let's get the pen, points in an n-dimensional space. This could be very confusing to folks. So let's go back here. We see that a scalar is just a one-dimensional vector space. It can only occupy things there. But if we think about a vector and we have n dimensions, so let's draw a one dimension here, and this is, let's say this is the x-axis, and don't call it x-axis because it gets confusing when you start using x-axis. And you can occupy spaces here, so 0, and this is negative all the way to negative infinity, and this is all the way to positive infinity here, so 1 and negative 1. So to your right, we're going to positive infinity. To the left, we're going to negative infinity. Now, if we just occupy uh, a point here, you can just have one, but that's a scalar. And we know scalars and vectors are different, right? So if we think about, let's think about if we want to write a vector in this number space, in something that we might be very familiar with, a two-dimensional vector space here, or a three-dimensional vector space would be, let's say you have, let's just do, let's do 1, comma 3. If I gave you this to say plot this on the number line, what would somebody do? What would you do to plot this, right? You might do something like, okay, so now let's add a new space here, a new dimension. And if we have our numbers going in this dimension and we want to plot 1, 3, so we know, so this is 1, 1, 2, 3, this is 3. We might have a point here, and this point is 1, 3. All right. Well, remember 1, 3. If we can see what this 1, 3 is, it's just a vector, a collection of tuples. So in this case, it's just 2 plotted on a 3D on well, this is a 2D vector space because we have 2 dimensions here, right? So this is a 2D vector space. Now we can have a point. Well, you might say, but yeah, we have x axis, we have y axis. If you've done any little bit of math beyond high school level, even in some high schools, you will know of the y axis, right? Which is kind of the axis that goes up. So your y axis. And in this case, y would give us 3 dimensions. So you might have something like 1, 3, 5. And you can plot that. You can imagine plotting this on the y axis somewhere here where you account for x, y, and z. So this would be, let's say, 1, 3, 5. And this point here would be 5, would be the point on the y-axis. So here, this would be my vector. And you might say, but well, why stop just at 3 dimensions, right? The human mind cannot think about this, but you can have a 4 dimension where you have 1, 3, 5, 8, right? And then 8 might represent something on another dimension, but visually we can't really draw it here. But you can see intuitively, hopefully intuitively, you can see how this begins to make sense, right? So the representation of a vector is just an ordered collection of numbers. But if you think about it as what's really happening is, one, this is, if we're representing this is the representation on, let's say you start with a scalar, which is 1, right? This is just a representation on a number line, just on a real number line like this. You can just represent 1 point. And then if you go above, two. So a scalar is just a singular vector, right? If you go to the next one where you have 1, 3, this is if this is two dimensions, so you can represent this on a two-dimensional vector space with x and y coordinates. If you go to 3, you can represent this on a three-dimensional vector space x, y, z, right? Just keep going to higher dimensions, and you can keep visually. The human mind cannot think of how we represent this visually, but the goal of vectors and all of this is not it's not the visual representation. It's just the algebraic structure that we use for computation. But I try to break this down so folks can get hopefully an intuitive understanding of how we get to this. All right. So um, again, going back to that definition here, points in an n-dimensional space. So we can have points in an n-dimensional space. Nothing limits us to 2 or 3 or 4. We can go to 1, let's say 3, 5, 8, dot, 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 all the way to n, right? And this would be our n-dimensional space that we can have points in this space. Now, if you had a way of visualizing this, the human mind can, again, I'm just repeating this over and over, but to really hit it home, the human mind can visualize a point on a single number line. We can visualize a point on xy coordinates, which is a 2D space. We can visualize point in a 3D space, but by the time you start going to 4D space, we can visualize it, but it doesn't mean that it's not a useful construct. It's a very useful construct all the way to n dimensions. You can have as many dimensions as you want. So points that exist in that space, this collection of it is what we call a vector. You might say, but why is a vector useful? Or where is this useful as we think about machine learning or computation? Just a really quick example, and this video is not really meant to give us those examples, but think about the representation of colors in computation. Colors are basically, I think it's RGB or something, red, green, and blue. A combination of that forms every single color. So you might have something like 270, 106, and 97. This will give you a specific color. Well, what is this color? This color is a point in this vector space. Well, I don't want to call it vector space anymore. In a 3D space. All right. So the computer, if you say whatever color you're seeing on your screen, behind the scenes, the computer represents it as a vector, which has three points, because a combination of red, green, and blue in the different concentrations will give you every color that there is. At least for the most part, I think that's the concept. So if you think about an image, well, now we just have a bunch of colors that we were dealing with, or a video is just a bunch of colors and points on the screen, and that's why vectors and scalars and matrices, which we're going to see next, become very, very relevant in computation. So let me just cancel that just so we keep it clean. All right. So now, hopefully, we have an intuition of what a vector is, and we have an understanding. Now, if we were to build the next level up from vectors, is we have a matrix. Let's get a pen here. If we build up from a vector, we are going to have uh, a matrix, or the plural is matrices. So what is a matrix? Again, you can see one construct builds the next construct, and it keeps building the next construct. So intuitively, a matrix is just going to be a group of, guess what, vectors. All right. What is a matrix? Is just a group of vectors. And there is just one catch with it, right? Because we see vectors can have different dimensions, 3 dimensions, 4 dimensions, n dimensions. And if you're going to take a collection of that and group them together, the only caveat for it to be a matrix is that those vectors all have to be of same dimensions. That's the only catch for you to have a matrix. So take a bunch of vectors that we have. Again, what's a vector? It's a collection of scalars. So a collection of scalars, you put them into a bucket, you form a vector. You take a collection of vectors of the same dimension, so the same length. Dimension is just basically the length of a vector, and you have yourself a matrix. So if we were to represent this, what we've seen here is Let me actually go back and put this here because this will be kind of something we reference. So here we have a scalar, and a scalar is 1. All right. Um, and from there, we had a vector, and you can have the vector linearly, I mean, horizontally or vertically. In many cases, you'll see folks representing vectors vertically. So you might have a vector of two values, 1, 2, right? Or you can have it as represented as 1, 2. So depending on the textbook, you might have the representation a little bit different. So a vector is basically a collection of scalars or points in an n-dimensional vector space, right? So here is just two dimensions. You can have a vector being 1, 2, 3, all the way till n, right? That'll be points in an n-dimensional vector space or n-dimensional space. And then we've seen here that the definition of a matrix, and we're going to go back to that, is a collection of vectors, but the caveat being those vectors all have to be of the same dimension. So you might have a situation of something like, let's do 1, 2, all right? That's one vector, and then you might do something like 9, 7. All right, that's another vector. So a matrix is a collection of vectors of the same dimension. So this is all two-dimensional vectors we've collected. Let's try another example here to see what a matrix is. Let's say we had a vector of 1, 3, 8. So this is a vector of how many dimensions? 3 dimensions. All right, we have a collection of that. So this first row is my first vector. Now let's put in another vector. Let's do 7, 6, 2. All right, so this is my second vector. Again, the caveat is that the dimensions all have to be the same. All right, so here we have a matrix, which is just a collection of n-dimensional vectors. What I cannot do is to have a matrix that has, let's start again, that has a vector of 0, 1, and then I have, so this is my 1 vector, and I come in here and have another vector of, let's say, 7, 6, 3, 1. All right, doesn't work. This doesn't work. Why? Because the dimension here in this first one is not the same as this dimension in the second one. This is missing. All right, so to have a matrix, you have to make sure that the vectors, the collection of vectors that you have building up the matrix, are all of the same dimension. That's the main requirement to have a matrix. So you can see a situation where we have a matrix. Let's get our pen back. Where we have a matrix of something like 1, 7, all the way to n. And then, well, let me actually not do it this way. Let's do it this way. Um, because with matrices, you list the columns first, and then the rows are coming second. So let's say we have our first vector in here, 1, which is 1, 3, 5, 9, all the way to n. All right. Now we have the next row, which is 1, 4, 5, 7, all the way to n. Remember, they all have to be the same dimension. So we're ending at n here, right? And we keep repeating this. We can have 1, 8, 6, 2, all the way to n. So the rule of having a collection of vectors of the same dimension is being met. We can repeat this all the way to where we get to n, or we get to m, 8, 3, 7, all the way to n. All right. So we've gone to the right by n, and that's 1. So this is 1 vector, and then we have m of those collection of vectors in our matrix. So this matrix is you usually start by listing the rows and then the columns. So you go by, so this is an m by n matrix. All right, so this matrix is an m by n matrix, where n represent the rows, and n, which is the going to your right, will represent the columns. Right, let's just do columns as COL. So that represent the columns. And sometimes you might hear this being called as this is the order of the matrix, and this the number of columns would be the dimension. And I've used that already, the dimension of the matrix. All right. So an n by m matrix, this is basically what it is. Again, it's a collection of vectors. All right. So this is our intuition. Now, the next uh, abstraction above matrices, which we've seen, is uh, so let's just do put that in here. So 1 all the way to n, 2 all the way to n, and then we come here m all the way to n. All right. So that's basically what we saw. And in this example that we've seen, this is an m by n matrix. And we're going to put in some more color to this as we go. So we have a scalar, we have a vector, and we have a matrix. Now, I'm sure we can imagine the next thing we're going to abstract on top of this, right? If you can take a bunch of scalars and put into a bucket or into a group, an orderless, and you have a vector, you take a bunch of vectors of the same dimension, you group them, you have a matrix. You can now imagine that if we take a bunch of metrics and we group them together, we're going to have something. And that's what we end up with. We end up with a tensor, right? So if you take a bunch of matrices, you group them together, you're going to end up with a tensor. And the way we're going to visualize this, and this is kind of fun to visualize, I hope I do it justice here with my visualization, is so think about this as being a matrix. What happens if we take a collection of this? All right. So what do we end up with? We end up with a tensor. So which again is just a collection of matrices. So let's see if we can do this. So let's start with a scalar, which is 1. All right. Now we have a bunch of scalars to get a vector. So 1 is a scalar. Let's do this of n dimension. All right. So we've collected n things. And what do we end up with? This is our first vector. So this first entry is 1 vector. So let's go to 2. That's our second vector. Let's go to 3. That's our third vector. They're all the same dimensions. All right. So now what are we building? We're building a matrix. So if we just add this all the way to m, and then we go all the way to the same dimension, what do we have? We have a matrix. All right. So if we do that, let's cancel these entries. What do we have? A matrix. And what is the dimension of this matrix is n. So it's actually an m by n matrix. So m rows and n columns in this matrix. Now, what happens when we group a bunch of these matrices together? All right. What happens when we group a bunch of these matrices together? This is where it gets to be fun. So let's put again another matrix here. Let's just build another matrix here to the right. And this is going to be, so let's say this was, I'm going to write this so it's very clear for us. So this is 1, right? So this is on our side here is 1. Let's specify this one. So let's do 1 here. This is another matrix. And we're going to go all the way to n. And then we have 2 all the way to n. We have 3 all the way to n. We have m all the way to n. This is our second matrix. Now, what happens when we take a collection of this, right? And so at some point, we're going to have here 1 all the way to n, 2 all the way to n, 3 all the way to n. And then we're going to have m all the way to n. All right. And then we take a collection of this. So we're closing this collection. We take a collection of this. Now, this collection of matrices gives us a tensor. And let's say we have this is our first matrix, this is our second matrix, all the way to this is matrix number k. So there are k matrices in this collection. Now we have a tensor, and the tensor here would be a k by m by n tensor. All right. So n is what the dimension, m is the row. Remember, we always the rows always come first when we write them. So the way you read this is this collection. There are k things in there, and what thing is it? Matrices. Well, what is in that matrix? The matrix is m. The m rows in each matrix, and what's the dimension of that matrix? What's the dimension of the vectors in that make up the matrix is n. It's a little bit confusing, but you can see that these are just building blocks, right? So one example I've used in this in the past is think about, let's say I have $100 in bills to give you, um, and the $100 is all made up of $1 bill. So I have a stack. Don't ask me why. Somebody would have a stack of $100, 100,000. Yeah, $100. It's just $100. $100 in 100 bills, and each of them is $1 bills. So $100 in $1 bills. So 100 of them. I can give you $1. If I just give you $1 out of that stack is a scalar. I've just given you one. Now, if I buy a bucket and uh I put $1 bill, 10 of them into that bucket. So 1, 2, 3, 4, 5. Let's just do 5 into that bucket. Let me clean this up so it's cleaner, because I think this is it's an interesting concept. So if I start off and I just give you $1 bill, that is scalar, just one. Now, if I take a bucket and I put 5 $1 bills in there, 3, 4, 5, and I give that to you, that's a vector, because we're taking a collection of scalars and we're giving a vector, right? There could be n dimensions there. I could, yeah, let's not even go into that for now. Then if I choose to say, hey, I'm gonna give you 5 of these buckets, right? So I take 5 of those buckets now and I give them to you, or like this, 3, 4, 5, and I just take 5 of those buckets and I put them in a bucket and I give them to you. So here you have a scalar, you have a vector, you have a matrix, right? And now if I'm trying to do a tensor, guess what? I can just create a whole bigger bucket and I say, okay, I'll give you 5 of the matrix buckets, right? So now I'll take this bucket. So this bucket, this matrix here, and I just simply take a collection of 5 of them, or how many of them I want, and I give them to you. And each of these has $1 bills. And there should be 5 in there for all of them. There should be 5, because otherwise it messes up the definition of matrix. So let's do 5. All right. So now this is a matrix, and now this is a tensor. I could have as many matrices as I want in this tensor, in this bucket, in this bigger bucket, and that's my tensor. So it's just a multi-dimensional collection of matrices. Visually, it's hard to see it when you draw it on a number line, but if you think about it as just collections and buckets, where a bucket can be in a bucket, can be in a bucket, I can have a bucket of. So nothing stops me from taking this bucket of tensor, this outer bucket, and putting it and taking a collection of this into a higher dimensional bucket, and taking that dimensional bucket and putting it into a collection of that and putting it into a higher dimensional bucket. Intuitively, that's exactly what we're saying here when we define things this way of matrices and vectors and such, right? So hopefully, let's uh, let's put this the dollar example. Hopefully, this idea of a dollar example makes sense, right? If you have $100 in $1 bills and you just give somebody $1 bill, scalar. If you take $1 bills, 10 of them, and put it in a bucket and give it to somebody, that's a vector. It's a collection of scalars. If you take that collection, if you take a collection of buckets that holds $1, $10 bills, and you give it to somebody, give them 5 of that, now you're giving them a matrix. If you take a collection of the matrices you've given to somebody, now you have a collection which is a tensor. So a tensor is just a collection of matrices. All right, there are a couple of things that I want to touch here before we wrap up with the lecture today. So tensors are kind of interesting. As you've seen, we've seen a vector, a scalar leads to a vector leads to a tensor is leads to cubes or things above tensors. Um, yeah, there are maybe a couple of things. There's really nothing above a tensor at this point. I think some people might use the term cubes, but cubes are just tensors of higher dimensions as well. So the thing I want to call out is this whole concept of ranks, right? So if you think about, and this might come across when you're dealing with this. So if you think of, let's put it this way. If you think of, so let's go back to our lecture here, and let's put tensor. A tensor is basically a collection of metrics. So this is a matrix, 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 and I think we know what the matrix is by now. So take a collection of that, any for any dimensions, you have a tensor, just basically a collection of metrics. Now if you have a one-dimensional matrix in your tensor, you might end up with a scalar, right? So a tensor is really the abstraction of all of that, and so we might end up with something like this. Let's go back here. Let's just do tensor one more time. So in the world of tensors, we might end up with something like this, and it completely makes sense. So let's do tensor. You might have something like 10, right? What is this? Well, this is a tensor. You might say, well, Fro, I got you. That's a scalar. Yeah, you're right. It's a scalar because it's just one value, but also it's a tensor of just one by one, right? So one by one tensor, and it's still a scalar. All right. So here we say this is of rank. This is a tensor of rank 0. All right. Then if we have something like this, if we have something like x1, x2, all the way to xm, right? What is this, right? What is this a construct here? You say, okay, I recognize that. That is a vector. It's just a collection of tensors, and you're right. Sorry, it's just a collection of scalars, and you're right. This is a tensor, it's a vector, but it's still a tensor of m by 1. And what this is a tensor of rank 1, right? And we'll define exactly what a rank is, because somebody might say it's a tensor of rank 3, and it's intuitively it's a little bit confusing. And that's what I want to clear up here before we wrap up the lecture. So that's a tensor of rank 1. As you can imagine, now if you have a matrix, which we've seen before, so you might have a matrix of A1, A12, all the way to A1, N here, and then you come down and you have all the way to AM, a 1, and then you might have AM2 all the way to AMN. All right, so that's an M by N matrix, right? So this is an M by N matrix. I think we're already familiar with that. And what is it also? Is a tensor of M by N. Remember the rows and columns, right? Start with the rows and the columns. And what is this again? This is the order. And this is the dimension, right? So this is the dimension of it. So, and this is still a tensor. But this tensor is of rank, you might guess, it's not of rank n, it's not of rank m, right? N or m is not of it. It's of rank 2. Now, why is this one of rank 2 and this one above is of rank 1? What is it that is different? Let's give one more example and then we'll see how ranks come about. All right, so let's go with the example of a tensor. So we're taking our metrics here, and now we have started with scalar, scalar, vector, matrix. Now we're going to build a tensor. So let's have a tensor, and I'm going to spare everyone the details here of of trying to write out a matrix in here, but just assume that we have a matrix in here. So this is a matrix. This is our matrix 1, right? And then we have another matrix here, matrix 2. And we have how many of these matrices? We're going to have k of these matrices. So all the way to matrix k. All right. And a collection of that. So we're collecting all those matrices, and that gives us a tensor. All right. And the way we're going to write this tensor is this is a tensor of, this tensor will be k by m by n. All right. So there are k matrices, right? So you always start with the outer dimension and you read it in. So there are k matrices we've collected, and each matrix has m. If you look at each matrix, it has m rows. So think about it as rows and n columns. All right. And n columns. So this will be m by n. And there are k of that. And you can take a collection of it. You can have a tensor of y by k by m by n. Nothing stops you from doing that, right? So it'll be a collection of y tensors, and and that each tensor inside would have k tensors. Well, would have k matrices. So y tensor. So if you take a collection of y tensors, and each tensor has k matrices, each matrix has m rows and n columns, this will be it, right? So you can keep going to infinitum with this. There's really nothing that stops you from there. But this particular one, can you guess what the rank for this would be? This is of rank 3. All right. So, and to be specific, I'm not talking about this last one here. I'm talking about a tensor of k by m by n, right? Is of rank 3. Now I'm sure we can start seeing how we get to ranks. Rank has nothing to do with the dimension or the order, which is basically number of rows or columns, right? Rank is really the number of independent or linearly independent components of the matrix or the tensor. So let's just define that here. Rank equals to number of linearly independent components of matrix or tensor. Because to a certain extent, every matrix is a tensor, right? Just like every square is a rectangle, right? But not every rectangle is a square. So every matrix is a tensor, but not every tensor is a matrix. So something to just think about when I used tensors and metrics interchangeably, it still makes sense. But you just have to specify what kind of tensor are you referring to, because every square I can call a square a rectangle. That's perfectly fine, right? But not every rectangle is a square. So but going back to our ranks, a rank equals to the number of linearly independent components of a matrix or a tensor. So here, what are the linearly independent components? We have n, which you can scale out. So n columns by m rows. So k by m, and we take care of that. All right. So that's 3. So 3 linearly independent components gives us a rank of 3. In this example here, we have just 2. So it's m by n. So it's a rank of 2, right? N could be 5. It could be 100. It could be a billion. That's the dimension of it. It has nothing to do with the rank. All right. And then the order of it, which is the number of rows, is m, which could be any number in this space. So but again, that has nothing to do with the rank. So if you look at the number of linearly independent variables, that's what the rank is. Intuitively, if this doesn't make any sense, go back into this example. Think about the number of, with the example we have here of, you can give me a dollar bill, or you can take 5 different dollar bills, put it in a bucket and give it to me, right? And that's a vector. And if we take 5 of those and put it into another bucket and give it to me, that's a matrix. And if we take 5 of those matrices and put it in another bucket and give it to me, that's a tensor. So think about the number of buckets that you're going to need at each point in time, and that gives you your rank. So here, how many buckets do I need? 1. So rank 1. Here, how many buckets do I need? 0. I can just give you a dollar bill. I don't even need to put in the bucket. So rank 0, right? For a vector, uh, how many buckets do I need? Well, I can put it in one bucket. I can take 5 different bills, put it in the bucket, and give it to you. So that rank is of rank 1. All right. For a matrix, now I can take 5 of the of those and put it in this other bucket and give it to you. Guess what? That's rank 2. Okay, because this outer bucket holds everything inside of it, and inside you have it. So just think about how many buckets do you have to go through to get to it. So I can go through this bucket, and as long as I go through this bucket 2, I've gotten into my, I can touch a dollar bill. It doesn't matter how many other buckets there are in the inner layer. I just care about how many buckets can you penetrate to get to your first dollar bill. So 1, 2, that's your rank. I think that's hopefully a good analogy there. In now, if you go to Tensor, how many buckets can you penetrate to get into your first dollar bill? You can go through 1, you can go through 2, you can go through 3, and you have your dollar bill there. So that's of rank 3, right? So rank is 3 in this case. This is just another way of intuitively understanding how to get to ranks in this sense, right? So if I took all of this bucket here, this outer bucket, and I took a collection of this, I took a collection of all of this, and put it in a higher bucket, well, the rank of that will be 4. Okay, it will be a 4 because it's now a collection of things of rank 3. So hopefully that makes sense, and that's how you get to ranks. Um, to ranks of things. So here, rank 1 is going to be a scalar. Actually, let's rank 0 is a scalar. Rank 1, let's be correct with what we say. So rank 0 is a scalar. Rank 1 is what? I'm sure we can guess it by now, right? Try in the comment section and see if you can guess this. So rank 1 is, if I can write, it's a vector. All right. Rank 2 is, you guess right, a matrix. Right. And then rank 3 would be what? They've used terms for this as cubes. People have used many different terms. Cubes is something I've heard, or just a tensor of rank 3, and then tensor rank 4, tensor rank 5. But that's basically what a rank is. So, and a rank is just the number of linearly independent components of a matrix or a tensor. And if you think about it as a bucket, how many buckets do you have to penetrate and touch in order to get to that dollar bill? 1, 2, 3, rank of 3. All right, guys. So hopefully this is helpful. This is some really foundational, elementary concepts to grasp if you're gonna work with machine learning, data science, AI of any capacity, or you might just be doing this from an abstract perspective in class, trying to understand vectors and matrices from whatever dimension you're coming from. Hopefully, this lecture has given you some intuitive understanding. I'm gonna hope to build on this in the next series of videos. They might not be sequential, to touch on some very, very foundational concepts in machine learning, like what is the process of taking, especially for natural language processing, taking text, and then you hear of vectorizing that text, and or tokenizing it and doing vectorization and stemming and lemmatization of a text in order to give you something that machine learning models like neural networks or GANs or can work on that, right? And those are some really, really good uh, areas in machine learning. But to take a text and to vectorize it, well, it helps for you to know what a vector is, right? Or what a matrix is, and all of that. And so hopefully this has given us that foundational concepts to understand. Now, I know this is a long video. If you want to pause, go back and rewatch it. And I highly recommend that. If you have a timestamp of this video and you want to share or put that in the comment section below on specific topics that make sense, I would highly, highly encourage that. I know these lectures tend to be very long, but uh, dialing into the area that makes sense to you, watch that, share it with anybody that might get value out of it, and we're gonna keep building on this as we go into our future lectures. As always, again, thank you for joining and being a part of this channel. I really appreciate you and everyone who watches to the end. Like it and subscribe it if you find value out of our lectures. You have been very, very awesome. I have been through, and I will see you in the next lecture.